Okay, so in this video, we're going to talk about what actually happens when acids and bases react. And you've already talked with me about these neutralization reactions, and we're going to look more closely at them and how we use them in chemistry. So remember, a neutralization reaction is always when an acid and a base react. Every time, it doesn't matter what the acid is or what the base is, you're always going to produce a salt and water. The hydrogen of the acid combines with the hydroxide of the base to give you that water, and then the ions that are left behind combine to give you the salt. Remember, a salt is just any ionic substance. There are three types of salts. There are acidic salts, there are basic salts, and there are neutral salts. It all depends on what combines to make them as to which one of these categories it'll fall into. So, when an acid and a base are mixed, the stronger one determines the type of salt. So, if you have a strong acid mixing with a weak base, you're going to get an acidic salt. If you have a strong base mixing with a weak acid, you'll end up with a basic salt. If both your acid and your base are strong, you end up with a neutral salt. If you take AP Chem, I'll teach you what happens when you mix a weak acid with a weak base. But for our class, we won't get that complicated. All right, so what do acids neutralize? That's right, bases. And what do bases neutralize but acids? So if we look at this, write a neutralization reaction to produce zinc chloride. You know you're going to have an acid and a base. You know these things are going to have zinc and chloride in them. And the other parts are going to be a hydrogen and a hydroxide. So which one goes with which? Well, your metal is always going to go with the hydroxide. Your nonmetal is always going to go with the hydrogen. So if I wrote this reaction, I would have hydrochloric acid, because chlorine is my nonmetal, it's always going to go with the hydrogen, and zinc hydroxide, because the metal always goes with the hydroxide. Try this one. What salt would be produced from the neutralization reaction of barium hydroxide and acetic acid? And they show us right here what acetic acid looks like. Well, the hydrogen from the acetic acid is going to combine with the hydroxide to give you your water. So what would be left behind? Hydroxide's gone. Hydrogen's gone. You've got barium acetate left behind. Okay. Now, titrations are a chemical lab procedure that we use to determine the concentrations of solutions that are unknown to us. So basically what we do is if we have an acid or a base that we do not know the concentration of, we can titrate that unknown solution with the opposite. So if it's a base, we titrate with an acid. If it's an acid, we titrate with a base. But we have to know the concentration of that thing that we titrate with. What happens in these titrations, and I'm going to show you a little video of one, but what happens in titrations is you will start off with the pH of the solution you have that you don't know the concentration of. And as you add the opposite substance, your pH is going to change until you hit this midpoint. It's called the equivalence point. At that point, you now have equal amounts of acid and base, and you can start figuring out concentrations from there. So this is what a titration of sodium hydroxide and hydrochloric acid would look like. you would start with sodium hydroxide and its pH is 14. You would start adding hydrochloric acid into it and the pH would drop and drop and drop. And then all of a sudden you would have equal amounts of both here. And then the hydrochloric acid is going to start taking over to where you don't have any sodium hydroxide left. And your pH will end up at hydrochloric acid's pH. That's what a standard titration curve looks like. It could go the opposite way. If I started with hydrochloric acid and I was adding sodium hydroxide, it would look the opposite. That is the equivalence point. When you are titrating a strong acid with a strong base, this equivalence point is always going to be at a pH of 7. It will not always be at a pH of 7 if you've got a weak acid or a weak base mixed in here somewhere. That would be different. It would still look like the same graph. Your equivalence point would just be at a different pH. So then your end point would be the point at which a titration is stopped once your indicator changes color. So when you do these titrations, both solutions are completely clear. And you use an indicator that we talked about in the last video to tell you when your pH has gotten to that certain level. And whenever that indicator changes, that's when you would stop your titration and do your calculations. Okay, why would we do a titration? The whole reason we do a titration is to find the concentration. We want to find that concentration of the unknown substance. So the calculation we use is molarity times volume. Molarity times volume is always going to give you the moles that you have. So this formula writes molarity of the known times volume of the known equals molarity of the unknown times volume of the unknown. That's what the K and the U mean. Often I will write this as molarity of the acid times volume of the acid equals molarity of the base times volume of the base. It just helps me kind of keep it a little bit clearer. Either one works. When you take the molarity of a substance times the volume of that substance, you will automatically know how many moles you have of that substance. So what we're showing here is that equivalence point. When our moles of our acid equal our moles of our base, we're at that equivalence point. So let's look at some practice problems. If 52.7 milliliters of a 2.13 molar solution is titrated with 76.9 milliliters of a sodium hydroxide solution, what is the concentration of the sodium hydroxide? So here again, you'd have your volume and your molarity of your acid equals your molarity, which is what you're trying to find, times your volume of your base. And that's how it fills in. You use your algebra to solve for your molarity of your base, and it would equal that. I want you to try it on your calculator, see if you can get it. Okay, try this one. Pause the video and try to get to the answer. Okay, you're back. The answer of the concentration of sodium hydroxide is 1.87. This is how you would have worked it out. Okay, try this one. Pause the video, find your solution. The answer is 18.1 milliliters. So if we were looking at this titration on a titration curve, this is what it would look like. You've got your pH on your y-axis, your milliliters of sodium hydroxide used, and we're starting with 100 milliliters of 0.5 molar HCl. We're going to use bromocresol green as our indicator, and phenolphthalein as our indicator. This will give us a good wide range of how our pH changes. Notice that our solution will start off yellow. It'll go to this green and blue, and as it hits this middle point, right, it would start to change to that pink. It gives us a good range. Here's another sample problem you can do. A volume of 108 milliliters of 5 times 10 to the negative third molar sodium hydroxide can neutralize 36 milliliters of nitric acid. What is the molarity or the concentration of that nitric acid? Use that same formula. Molarity of acid times volume of acid equals molarity of the base times volume of the base. And you get a 0.015 molar solution of nitric acid. Here's another sample problem. You've got barium hydroxide being titrated with hydrochloric acid. It produces barium chloride and water. Sample neutralization problem. Here's your data. According to this equation, adding 38 milliliters of 1.5 times 10 to the negative 2 molar barium hydroxide can neutralize 20 milliliters of hydrochloric acid. What is the concentration of hydrochloric acid? Use your same formula. Let me go back here for a second. I just clicked on this. Notice here though, for every 1 barium hydroxide, we get 2 hydroxides. So that means in order to neutralize it, we're going to need 2 hydrochloric acids. So we're going to have to pay attention to that. We're going to use the same neutralization formula, but we're going to multiply barium hydroxide's concentration by 2 because we have twice the concentration of hydroxide that we do of the barium hydroxide as a molecule. We still use this, but we had to double that concentration. And so we get a 0.057 molar solution of hydrochloric acid. Last concept, buffers. We're not going to do too much other than identify them. Buffers are a substance that help keep pH fairly constant. That doesn't mean neutral. So we use buffers in our body's system all the time because our pH within our body needs to stay fairly constant. It's right around a neutral value. But we'll use buffers even in chemical labs and biochemical labs. They're just a substance that helps us absorb some of that acid or base that we're adding to the solution so that the pH doesn't all of a sudden just jump. Buffers always consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. And what that does is that way you have substances in your solution that if I add an acid, the base part of it can pick it up. If I add a base, the acid part of it can pick it up. And that's what a buffer will do. All right, you've got an assignment on Canvas. I'll look forward to seeing you in our next class. Have a great day.